Good morning. First off, I need to apologize. I think I caught a cold somewhere coming here to Stockholm, so I hope my voice will last for at least another 20 minutes. But my name is Joost van Dijk. I'm a developer advocate at Yubico. Yubico is a company that creates the YubiKey. Anyone familiar with the YubiKey, perhaps? Ah, perfect, nice. But actually, I'm not going to talk about YubiKeys per se. I'm going to talk about Passkeys. There's a lot of fuzz about Passkeys lately, and also a lot of confusion. So my goal is to explain what Passkeys are and why they are interesting when you're dealing with API security. So let's skip the overview. I'm very happy to have seen the previous presentation because I think mine aligns very well. Here's the typical OAuth flow, the authorization code flow. Everyone familiar with this OAuth stuff? I guess because that's why you attended the previous presentation. So this is your user agent, like your browser, client application, your authorization server, your resource server. And it starts off with, oh, that's the wrong button, sorry. It starts off with, well, my pointer is not really working. Apologies for that. It starts off with this front channel flow. Then there's user authentication. Then there's an exchange of the authorization code for a token. Then there's the API request, and hopefully you're done. And we've seen all these technologies that will secure this flow. So there's places in this flow where an attacker can intervene and possibly steal your access token or your authorization code. And we've seen all these technologies, and there's actually a couple more here, that will protect you from these attacks. But if you look at all these specifications, there's one thing that is always out of scope, and that is user authentication itself. So user authentication is of course important because that's the step that is required prior to authorization. If you ask a user for authorization, the user first needs to be authenticated. So that's the step here, and that is declared out of scope from all the OAuth specs. So if you are putting energy in securing your OAuth flow, then you have the risk of letting your user authentication become the weakest link. So that's why I like to talk about Passkeys, because I think Passkeys are a perfect solution for securing the whole flow, including user authentication. So without further ado, what are Passkeys? So the short answer is a passkey is a more secure and also more user-friendly alternative to a password. We know what the problems with passwords are. So why is a passkey better? Well, first off, one of the design goals of a passkey is that it is phishing resistant. So if you have a phishing site, even if you have implemented a multi-factor authentication, it really depends on the exact method that you're using if that will be phishing resistant. So if you're using OTPs, for example, an OTP can be phished just as easily as a password. So you need something that is phishing resistant. And there is something that is phishing resistant, has been there for a long time, and those are user certificates. But they have vast deployment problems and usability problems. And the nice thing is that Passkeys, they use public key authentication, just like with a PKI system, but it doesn't require a certificate to be issued to a user. It's in that sense, it's more like SSH, if you know SSH, where you have just a private key and a public key. The public key is deployed at the server, and then from that point on, you can just authenticate using the corresponding private key. And Passkeys are similar. But they're also phishing resistant, and I'll explain in a moment why that is. But there's more to it, because let's say that there's a breach of your server, your authentication server. So if you're using passwords, that is a problem, because that may mean that your passwords can be reverse engineered. They can be published in a database. And with public key authentication, you can do that, but there's no use, because all the information that is stored on the server is public. It's the public key that is stored. So if that public key becomes known to everyone, that's not a problem, because it's public, right? And then for usability, it's also nice because everything is handled by your browser. You don't have to, as a user, you don't have to think of any secrets or worry that you're reusing credentials over different sites, because that is all done automatically. So, well, I'm talking too much, I guess. Yeah, we're back. So with Passkeys, every site that you're signing into will have a different public key. So there's no reuse of public keys anywhere. And lastly, it is possible to store your passkey on secure hardware, which is very interesting for example, for banks or government agencies that have this MFA requirement, and they really require your credentials to be stored on secure hardware so that it cannot be copied. So that really depends on your application, but that is something that is possible with Passkeys. And the good thing is it's not just more secure, it's also more user-friendly, because everything is done for you, right? And of course, how do you authenticate if you don't have a password? Yeah, well, that's simply using your finger, your face, or maybe a PIN, depending on what kind of passkey or where your passkeys are stored. And optionally, if you worry about backups, there's also the option of having your passkeys synchronized with some cloud storage, similar to what password managers do, but then not with passwords. So maybe just give a very short demo for people that are new to Passkeys. This is a demo site that we built at Yubico. And if I want to sign in, I click sign in with a passkey. I'm on a Mac, so I have a fingerprint reader here. If I touch my fingerprint reader, I'm signed in. Hello, Joost. And that's for a user, it cannot get any simpler than that, right? So it's a very boring demo. And I like boring demos when it's about authentication, because that means that it is easy, right? So let me introduce some terms. So these passkeys, where are they stored? Well, there's several options, and that's why there are several devices called authenticators. So an authenticator can be some secure hardware. So Yubico builds the YubiKey. So I have this keychain with like a USB security key. So that's where you can store a password, but you can also store it on your platform. So I can store it on my Mac. And actually, if I use Safari or Chrome, the latest version of Chrome, I can store it in my iCloud keychain. So it's also available on my iOS device, for example. But it really depends on your preference. So do you want to have it more secure, or do you want to have it automatically backed up, for example? So there's different kinds of places where you can store passkeys, and they are called authenticators. So roaming authenticators, like security keys, and platform authenticators that are built into your device. But there are also different kinds of passkeys. So we distinguish hardware-bound passkeys. Those are the passkeys you typically store on a USB device. So like a YubiKey, but actually it's defined in an open standard called FIDO. So any FIDO security key will work that way. But it can also be stored in something like iCloud or your Google Password Manager. And then we call that a synced passkey, because Google or Apple will synchronize those passkeys using the cloud. So everything is encrypted end-to-end, but it means that if you create it on your Mac, for example, it becomes available on your iOS device. So those are syncable passkeys. And in the case of Apple, you can also make a copy, actually. So there's a security trade-off there, because yeah, if you're a bank and you have like a PSD2 requirement of user credentials not being copyable, yeah, then obviously a copyable passkey won't fit, but a hardware-bound passkey will. So it's good to mention that whether you're using a hardware-bound or a syncable passkey, both are phishing resistant. And that is a very big win. So anyone that sees something peculiar about this login site, it looks like the one from Microsoft, but of course, if you look at the URL, that doesn't match. So this is obviously a phishing site. So how does a passkey protect against phishing? Let me briefly explain. So I'm not going to explain in complete detail, but because we're using public key cryptography and we have a public key stored on where it's called a verifier here, but that will typically be your relying party or your API resource server, or sorry, your authentication server, I mean. And you have a user that has like a FIDO security key. This public key authentication protocol that is being used, so this is not really FIDO, but it's conceptually the same because it uses a challenge response procedure where the verifier generates a challenge that is transferred through the browser to a authenticator, where the private key is used to sign the challenge. And if the public key is known to the verifier, they can verify the signature. So this is basic public key authentication. Now, what happens with the passkey is that your browser helps you in preventing phishing, because as a user, you may not pay attention to the address bar where the host name is, that may or may not be from Microsoft in this example. But your browser knows exactly what that is. And what your browser does is it will include what is called the origin, so basically the domain name of the relying party. It will include that in the signature algorithm. So that's done automatically for you. So that means that if you have a phishing site, the origin known to the real relying party and the phishing site will differ. And that means that the signature simply won't match what the verifier checks. So this is a very simple trick to prevent phishing. And because passkeys are supported by all major browsers these days, a passkey will protect you from phishing. Very important feature, I think. So how does this work? I'm not going to explain in too much detail, but your browser will implement something called OAuth N, which is an API. So that is standardized by the World Wide Web Consortium. And this API will either ask a roaming authenticator, like a FIDO security key, or your platform authenticator to perform this challenge response algorithm. And basically, it's only two JavaScript method calls you have. You have a create and a get call. What I illustrated in the demo was the get call. I was authenticating, so get is for authenticating. But you also need to make the public key known to the relying party. So that's where the create method is for. So create will create a new key pair specifically for that origin, return the public key to the relying party so that subsequently they can authenticate the user. So how do you implement this? Actually, we're talking about API security, so I say you don't. You just use a authorization server that implements passkeys. And I understand that Curity, for example, implements passkeys, but there are actually many more. And so check your authorization server, whatever you're using, if passkeys are supported. And if you're using like Microsoft Entra ID, that will support passkeys and many more, actually. So this is really an option you can use today to secure the user authentication part of your APIs. Let me diverse a little bit about some other stuff you can do with passkeys. So if you have a passkey stored on a roaming authenticator, like this USB security key, there's also a feature called attestation, which means that you can, as a relying party, check what the provenance of that security key is. So the make and model of that particular security key can be returned in this create call. So when you register your passkey, the relying party can ask for this information and make authorization decisions. So let's say that you're a financial institution and you have rolled out YubiKeys or other FIDO security keys to your employees, then you know that whoever will authenticate will be using this particular make and model. So you can actually check for that, so that make sure that someone's not using something else. And there's many people, or many companies implementing these roaming authenticators. So you can decide which one you trust and which ones you don't. So this is a nice feature. Here's an example of a YubiKey. So someone built like a viewer of the metadata that is hosted by the FIDO Alliance. And you can just look up the properties of any FIDO security key that is registered. So you can see, for example, is this particular USB authenticator using secure hardware? Is it certified according to the FIDO Alliance certification system? And you can make authorization decisions based on this. Excuse me. So let's take a look at how you can use this in your API. So let's say that you have defined a number of levels of assurance. So obviously, passwords are somewhat to the left. We know about the security problems. And we can go all the way to the right with hardware-bound passkeys, where you know that no one can make a copy. So you cannot share the passkey because it's stored on secure hardware. And there's many things in between. So the copyable passkeys, they will be less secure because you can make a copy. But still, also the copyable passkey is phishing resistant. OTPs, on the other hand, are not phishing resistant, so they are even more to the left. So you can build a spectrum of authentication methods that you can assign levels to. So let's say that you have an API that you want to secure, but you want to, let's say you want to allow copyable passkeys for some transactions, but for the highly secure transactions, you need to have a hardware-bound passkey. Well, you can use all these technologies together to do something that is called step-up authentication. So, please, another 5 minutes of my voice. So the authentication level that can be communicated with something called a authentication context class reference. So that's just another way of saying some policy that is in place for defining authentication levels. So if you go to your resource server, so you make an API call, and you pass this, let's say, a bearer token, then the response from the API could be that you have insufficient user authentication. And it is a standardized error message in a recent RFC that indicates to the client that you need to have a stronger authentication method performed before you can actually call the API. So let me finish with this example. So this is, again, the OAuth flow. You're doing some authentication. Let's say it's a low assurance authentication. You do your API request. Some low, so not sensitive API request will just return a 200 OK. But if you do another API request to a endpoint that requires this higher authentication, higher level of authentication, you will get a request that says, wait, is this the wrong? You'll say it will give you a 401 unauthorized. So that means that you have to get a new access token. So you're going to the authorization server again, but this time you authenticate with this high assurance, and this ACR claim will be included in your access token. And when you do the new GET request to the sensitive endpoint with the new token, you'll get a 200 OK. And this is the way you can implement step-up authentication using these different levels of assurance. So let me finish off with some key takeaways. Well, first of all, I'd like you to remember that passkeys are more secure and also more user-friendly, in particular that they're phishing resistant by design. Why could you use it in API security? Well, to prevent your user authentication process to become the weakest link. And it doesn't mean that you only need to use passkeys when you're doing API security with some high-level requirements. Because why would you ever use a password if you can use passkeys? So use passkeys anyway, and use something like step-up authentication if you need a higher level of assurance. OK, those are actually the three most important ones. So questions after next talk, I think.